Acids and bases. We've studied acids and bases before. So this table is a quick review of the properties of acids and bases. Acids are sour. They're lemons and citric. Fruit contains citric acid. And this is used also in candies. Sour candies contain acids. They feel like water. They don't feel any different. The pH is less than 7. They are clear and colorless with phenolphthalein. Litmus paper test is that litmus paper will turn red. They are corrosive, so they can cause chemical burns. So if you use strong or concentrated acids, you should wear gloves and safety goggles. And they conduct electricity because they produce hydrogen ions. So if you produce ions, you will conduct electricity. Bases, on the other hand, are bitter. You know this if you've ever got soap or shampoo in your mouth. They feel slippery. The pH is greater than 7. If they're mixed with phenolphthalein, they turn pink and clear. If it's a lot of base, then it's almost fuchsia pink. They will turn red litmus paper blue. They are also corrosive, which can cause chemical burns, so the same safety precautions have to be taken. And they are also electrolytes, and that's because they produce ions as well. They produce hydroxide ions. Basically, reactions for acids and bases is that an acid plus a base will make an ionic compound, some form of a salt, and water, liquid water. A lot of food products are acidic. Vinegar, tomatoes, apples, lemons, bananas. Milk is even slightly acidic. Hydrochloric acid that's in your stomach is extremely acidic. In terms of bases, baking soda, blood, soap, basically household cleaners, drain cleaner, ammonia, these contain bases. So the Arrhenius theory of acids and bases is that an acid is a substance that contains hydrogen in its formula and ionizes in water to produce one or more hydrogen ions. And that a base is a substance that contains OH in its formula and dissociates in water to form one or more hydroxide ions. However, there are some problems with Arrhenius' theory. So the acids actually form hydronium ions, not hydrogen ions. Hydronium ion is the H3O plus ion. And basically, this is what happens when the H plus attaches to water molecules. Some bases actually don't contain an OH. Ammonia is a base. It's a weak base, but it's still a base. And there's no OH in the formula, but it produces hydroxide ions. So we know that because it produces hydroxide ions, it's basic. Carbonate salts also act as bases. And Arrhenius acid-base solutions react only in water, but some acid-base reactions take place in other solvents. That has led to a revised theory of acids and bases, and Bronsted-Lowry came up with this, and that is that an acid is a substance that can donate a proton, whereas a proton is an H plus ion, not that positive subatomic particle. A base is a substance that can accept a proton. So you're an acid if you can donate an H plus ion, and you are a base if you accept an H plus ion in a reaction. Conjugate acid-base pairs. These are species that differ by an H in their chemical formula. When an acid is ionized and an H plus ion is removed, what's left is called the conjugate base. The stronger the acid, the weaker its conjugate base. The weaker the acid, the stronger the conjugate base. When a base accepts an H+, the new particle becomes a conjugate acid. The weaker the base, the stronger the conjugate acid, and vice versa. So when you're identifying conjugate acid-base partners, you're looking for two species, two entities that differ only by an H+ in their formula. And what is on the left-hand side of the arrow will be your acid or your base, and its conjugate partner will be on the right-hand side. So let's do a couple of examples. First example here, we've got acetic acid plus water to make the hydronium ion and the acetate ion. So identify the two species that differ by an H+. So here we have acetic acid and we have acetate. They differ by an H+ in their formula, but also H2O and the hydronium ion differ by just an H+ in their formula. So, because in this conjugate acid-base partner, we lose an H+, that makes this the acid, because it donated an H+, and that makes the acetate ion its conjugate base. If we look at the water and the hydronium ion, the water ended up accepting an H+, so therefore it is the base. And that makes the hydronium ion its conjugate acid. So one side you have the acid and the base, the other side of the arrow you have the conjugate partners. And you can actually represent these with letters. You can do A for acid, Ca for conjugate acid. So next example, we've got ammonia plus water makes ammonium and the hydroxide ion. So if we look at these, we see that ammonia and ammonium differ by only an H+ in the formula, but so do water and OH-. So going from left to right, NH3 gained an H+. If you accept an H+, that makes you a base. So base. That means the ammonium is its conjugate acid. Water lost an H+ in this reaction, so it was an acid. It donated it to the ammonia, and that makes the hydroxide the conjugate base. An important use of these pairs is buffers. So a buffer is a substance that basically you add to a mixture, a solution, and if you add either acid or base to the solution, it basically uses up any added H+ or OH- so that the pH doesn't change of the original solution. So a conjugate acid-base pair, a buffer pair, would a common buffer might be acetic acid and sodium acetate. Or ammonia and ammonium chloride. The conjugate acid part, if we look at the ammonium ion, I just want to prove to you that that is actually an acid. So I said ammonium was a conjugate acid, so that means it should donate a hydrogen ion, and it does. So here, ammonium will go to ammonia, and water will accept the hydrogen ion. So if you are a conjugate acid, you will donate an H+, and a conjugate base will accept an H+ in a reaction. An amphoteric species. These are substances that can act as an acid or a base, so they can either accept an H+ when they're with an acid, or they can donate an H+ when they're with a base. Common example is water, but you can also have hydrogen carbonate ion. If you are reacting with a base, it will form carbonate, donate its H+, but if it's with an acid, it can accept an H and form carbonic acid. Water is a conjugate in a conjugate acid-base pair. So we have something where water can react with itself. Two molecules of water react together to form hydrogen ions or hydronium ions and hydroxide. So what would the equilibrium constant look like for this reaction? You can only put AQ and G species in a K expression because the liquids and the solids don't change enough. They basically stay constant. So our K for this would be the hydronium ion, or the hydrogen ion, times the hydroxide ion. This is a special reaction called auto-ionization of water, meaning this happens all the time in a sample of water. Two molecules will react with each other, and it will ionize and form a hydronium ion and a hydroxide ion. It happens very slowly, and it's a very small amount. So this is a special and a very important K expression, and we call it the ion product constant of water, and we give it its own symbol, Kw. It's important because we can use it to determine the hydrogen ion concentration and the hydroxide ion concentration, and we use it to determine the pH of a solution. By comparing the resulting concentrations, we can identify whether a substance is acidic or basic. So Kw is equal to the hydrogen ion or the hydronium ion times the hydroxide ion. And we know that the Kw value is 1.0 times 10 to the negative 14. So this is a known value. We know that we produce one hydronium ion and one hydroxide ion for every 2 molecules of water that react. So at room temperature, we have hydrogen ion concentration or hydronium ion concentration equal to the hydroxide ion concentration in pure water. So if we make these X, we have X times X, equal to 1.0 times 10 to the negative 14. So X squared is equal to 1 times 10 to the negative 14. So if we take the square root of both sides, X is going to be equal to 1 times 10 to the negative 7 moles per liter. That is the concentration of the hydronium ion, or the hydrogen ion concentration, and the hydroxide ion concentration at room temperature. Now, this tells you that the hydronium ion and the hydroxide ion have an inverse relationship, because multiplied together they equal that amount. So if the hydrogen ion concentration goes up, the hydroxide ion concentration would go down. If the hydroxide ion concentration went up, the hydronium ion concentration would go down. So if we have a situation where the hydronium ion concentration is greater than the hydroxide ion concentration, we will have an acidic solution. If the hydronium ion concentration is equal to the hydroxide ion concentration, then it will be neutral, pH of 7. And if the hydronium ion concentration is less than the hydroxide ion concentration, then we have a basic solution. So we can use this Kw expression to figure out, if we know the concentration of, let's say, hydroxide ions or hydronium ions, we can predict whether or not our solution is acidic or basic.